Potential difference and electric fields, past paper questions. 2003, question 8. Two parallel plates, R and S, are connected to a 2-volt DC supply as shown. An electron is moved from plate R to plate S. The gain in electrical potential energy electron is, well, the gain in electrical potential energy is exactly the same as the work done. W is equal to QV. We should know the charge on an electron because that's given within the datasheet. So that's 1.6 times 10 to the negative 19 multiplied by a potential of 2 volts, giving us an overall amount of work done as 3.2 times 10 to the negative 19 joules. Work done is equal to the electrical potential energy gained, and so our answer is C. 2005, question 7. 1 volt is equivalent to 1 joule per coulomb. Also C. 2005, question 8. A potential difference of 5,000 volts is applied between two metal plates. The plates are 0.1 meters apart. A charge of 2 millicoulombs is released from rest at the positively charged plate as shown. The kinetic energy of the charge just before it hits the negative plate is, well, here we have the work done in moving the charge being equivalent to kinetic energy. So we say W is equal to EK. Our work done is equal to QV. We're told that this is a 2 times 10 to the negative 3 coulomb charge with a potential of 5,000 volts. 2 times 10 to the negative 3 multiplied by 5,000 is simply equal to 10 joules, and so our answer is D. Here we have another question. This one's from the old higher 2008 question 8, but we see exactly the same process where they're equating the work done to the kinetic energy of the particle. W is equal to QV. Charge on electron, can't remember what it is, it's on the datasheet, 1.6 times 10 to the negative 19 coulombs, multiplied by a potential of 2 times 10 to the 3, giving us a value of 3.2 times 10 to the negative 16 joules. E. 2009, question 7, again very similar. Notice in these questions we're given a value of the distance, but we're not actually using it. In this question we're told the kinetic energy of the charge just before it hits the negative plate is 8 joules. So we're given the kinetic energy first, and we're asked to find the potential difference between the plates. Same thing applies though. EK is equal to W, which is equal to QV. So we say 8 joules is equal to our Q, our charge, which is 4 times 10 to the negative 3 coulombs, multiplied by our potential, which is what we want to find. V is equal to 8 divided by 4 times 10 to the negative 3, which is equal to 2.0 times 10 to the 3 volts. So our answer is D. 2010 question 7 is a definition. We're looking for the definition of potential difference between 2 points. Well, in order to do the definition, we can look back at the equation. W is equal to QV, which means V is equal to W over Q. So potential difference is the energy per coulomb. So if we have a look at the options, we can see the work done in moving 1 coulomb of charge between the 2 points is our correct answer. 2006, question 24. Diagram below shows the basic features of a proton accelerator. It is enclosed within an evacuated container. Protons released from the proton source start at rest at P, rest, important term. A potential difference of 200 kilovolts, that's 200 times 10 to the 3 volts, is maintained between P and Q. What is meant by a potential difference of 200 kilovolts? So we could refer back to that multiple choice question we just did. Potential difference of 200 kilovolts means 200 kilojoules of energy is transferred to each coulomb of charge. By the electric field. Or the supply. In part B, we're asked to explain why protons released at point P are accelerated towards point Q. Well, there's a number of different answers here, but they all start basically at the same point in saying that protons have a positive charge. We could then simply say that they are attracted to the negative terminal, or the negative plate. We could also say that charged particles in the electric field experience a force. We could say that the positive charge moves within the direction of the field. But probably the most common answer would be this one here, that the protons are attracted to the negative terminal of the accelerator. In part C, we're asked to calculate the work done on the proton as it accelerates from P to Q, and the speed of the proton as it reaches Q. Well, first of all, we have a look at the work done. So W is equal to QV, which is equal to 1.6 times 10 to the negative 19, because that's the charge on a proton, which we would get from the datasheet, multiplied by our potential, which is 200 times 10 to the 3 volts, giving us a value of 3.2 times 10 to the negative 14 joules, and that's for part 1. For part 2, we're asked to calculate the speed of the proton as it reaches Q. Well, we know that the work done is equal to the kinetic energy. So we calculated before that the work done was 3.2 times 10 to the negative 14 joules, and that's equal to 1/2 mv squared. In order for us to be able to do this question, we need to find the mass of a proton, and the mass of a proton is found on the datasheet as 1.673 times 10 to the negative 27 kilograms. So we say that 3.2 times 10 to the negative 14 is equal to 1/2 multiplied by 1.673 times 10 to the negative 27 multiplied by our velocity squared. This gives us a value of v squared being equal to 3.83 times 10 to the 13. V, remember it is v we're trying to find, not v squared, is 6.2 times 10 to the 6 meters per second. We're told that the distance between P and Q is now halved. What effect, if any, does this have on the change in speed of the proton as it reaches Q? We have to justify your answer. So justifying your answer is either by a calculation showing a relationship and equation. Well, the distance between P and Q has changed, but when we calculated kinetic energy, we used the relationship W is equal to EK. That is, QV is equal to 1/2 mv squared. And D, distance, doesn't appear anywhere within here. So there's going to be no effect as Q and V are constant. That would be absolutely fine. We could add in here and m, which is the mass of the proton. 2007, question 24. We have another electric field, and we're told an alpha particle traveling at a speed of 2.6 times 10 to the 6 meters per second passes through a hole in plate A. The mass of the alpha particle is 6.64 times 10 to the negative 27 kilograms, and its charge is 3.2 times 10 to the negative 19 coulombs. In part A, when the alpha particle reaches plate B, its kinetic energy has increased to 3.05 times 10 to the negative 14 joules. And we need to show that the work done on the alpha particle as it moves from plate A to plate B is 8.1 times 10 to the negative 15 joules. Lots of information here, so you might want to highlight the important parts. So we know that the alpha particle is traveling at 2.6 times 10 to the 6 meters per second. The mass, charge, the kinetic energy that we have increased to, and what we're trying to find out, the work done. Now, because we're given the value of what the answer is supposed to be, we're not going to get any additional marks for that. Okay, so let's work this out. So at A, we have that kinetic energy that we can calculate. So EK is equal to a half mv squared. That's 1/2 multiplied by the mass, which is 6.64 times 10 to the negative 27, multiplied by the velocity that we're told in the question, 2.6 times 10 to the 6 squared. Remember to square the number. Gives us a value of 2.24 times 10 to the negative 14 joules. So that's the kinetic energy at point A. We know that the kinetic energy is increased to 3.05 times 10 to the negative 14 joules by the time it reaches plate B. So the work done is equal to the increase in kinetic energy, or the EK gained. So that's going to be whatever we had at the end, 3.05 times 10 to the negative 14, take away what we already had. Which is equal to a value of 8.1 times 10 to the negative 15 joules. In part B, we're asked to calculate the potential difference between plate A and plate B. Well, we know that the kinetic energy gained is equal to 8.1 times 10 to the negative 15 joules, and that's the same as the work done. And work done is equivalent to QV. So 8.1 times 10 to the negative 15 is equal to our charge given in the question as 3.2 times 10 to the negative 19 multiplied by our value of the potential, V. So V is going to be equal to 8.1 times 10 to the negative 15 divided by 3.2 times 10 to the negative 19, which is equal to 2.5 times 10 to the 4 volts. We'd also allow, with significant figures, 25310 volts as well as 25300 volts. In part C, we're told the apparatus is now adapted to accelerate electrons from A to B through the same potential difference. How does the increase in kinetic energy of an electron compare with the increase in kinetic energy of an alpha particle? Now, what's important to note is that the electron has a different charge. Also, an electron has a different mass. So we have the same potential difference of the field. However, the charge is smaller. So that means the work done is going to be smaller, that is W equals QV is going to be smaller, and therefore the increase in EK will be less. Now, one thing important to note here is just because the increase in kinetic energy will be less, it doesn't mean the velocity is necessarily going to be less, because an electron has a much smaller mass than an alpha particle. Revised Higher Paper 2012, question 23. An ion propulsion engine can be used to propel spacecraft to areas of deep space. A simplified diagram of a xenon ion engine is shown. We have a positive metal grid and a negative metal grid, therefore we have a field existing between them. We have positive xenon ions, and then those ions are accelerated and emitted as an ion beam. The xenon ions are accelerated as they pass through an electric field between the charged metal grids. The emitted ion beam causes a force on the spacecraft in the opposite direction. The spacecraft has a total mass of 750 kilograms. The mass of the xenon ions is 2.18 times 10 to the negative 25 kilograms, and its charge is 1.6 times 10 to the negative 19 coulombs. The potential difference between the charged metal grids is 1.22 kilovolts. So there's lots of important information here, and what we should be doing is highlighting each of those bits of information ahead of doing our question. Remember, the first step in every calculation question is writing down what you know. So in part A, we're asked to show that the work done on a xenon ion as it moves through the electric field is 1.95 times 10 to the negative 16 joules. Well, in calculating the question, we know the equation that we need to use is W is equal to QV, which is equal to the charge on the xenon ion, which is 1.6 times 10 to the negative 19, multiplied by our potential, which is 1.22 times 10 to the 3 volts, because it's measured in kilovolts within the question. This gives a value of our work done to be 1.95 times 10 to the negative 16 joules, as required. QED. In part 2, we're said, assuming that the ions are accelerated from rest, calculate the speed of the xenon ion as it leaves the engine. Now, what we had there for the value of the work done is really important for us to note down. So let's remind ourselves that W is equal to 1.95 times 10 to the negative 16 joules. So we can say that our work done is equal to our EK. So 1.95 times 10 to the negative 16 is equal to 1/2 mv squared, which is a 1/2 multiplied by the mass, which we're given within the question. It's 2.18 times 10 to the negative 25, given the question here. And we're multiplying that by velocity squared. So 1.95 times 10 to the negative 16 is equal to 1/2 2.18 times 10 to the negative 25 multiplied by v squared. So v squared is going to be equal to 1.95 times 10 to the negative 16 divided by 1/2 of 2.18 times 10 to the negative 25. And the value of v is going to be the square root of this. So v is equal to 4.23 times 10 to the 4 meters per second. In part B, we're told that the ion beam exerts a force of 0.070 newtons on the spacecraft. You need to calculate the change in speed of the spacecraft during a 60-second period of time. Well, this is actually going back to our first unit, and we're looking at impulse and change in momentum. So Ft is equal to mv minus mu. Remember, we were told that we started at rest, So 0.07 multiplied by 60, so our time, is equal to our mass of 750 kilograms. Remember, it's the mass of the spacecraft we're using here, multiplied by our velocity, minus 750 multiplied by our initial velocity, which was 0 because we started at rest. So we end up with a value of v being equal to 0.07 multiplied by 60 divided by 750, which is equal to 5.6 times 10 to the negative 3 meters per second. We're told that a different ion propulsion system uses krypton ions, which have a smaller mass than the xenon ions. The krypton engine emits the same number of ions per second, therefore the same work done, at the same speed as the xenon engines. Which of the two engines produces a greater force? Well, in order to find that, we need to think about what's happening to the change in momentum. So the change in momentum for the xenon ions would be greater, as the xenon ions have more mass. And that's because momentum is mass times velocity. And we're told here that the velocity is exactly the same. So because the change in momentum of the xenon atoms are going to be greater than the krypton atoms, krypton ions rather, and that means that the impulse from the xenon ions will be greater, and so the force from the xenon engine must be greater.